This is the typical life cycle for an AI feature on the web. When a user requests text processing, data packets travel to a distant server, wait for a model to respond, and return across the network. This architecture creates three persistent bottlenecks. Product teams accept a linear variable cost, high network latency that limits real-time interaction, and the requirement that user data must leave the machine. Chrome has introduced an alternative by shipping the Gemini Nano model directly to the user's desk. This 4 GB instruction-tuned model loads into the local GPU instead of waiting for a remote server. Chrome moves the inference step into the browser, creating a local runtime for the computational work. Cloud LLMs charge per call. Chrome's on-device execution drops this marginal cost to $0. Cloud latency averages 200 to 2,000 milliseconds. Local execution drops that to 0 milliseconds. Finally, rather than requiring data egress, information stays on device. Standard APIs require strict per-user rate limits and queuing to manage server load and costs. Local execution is unmetered, limited only by the memory and compute power of the user's hardware. When inference is free and network latency is removed, the design space for web applications expands. Features previously restricted by high per-call costs, like per-keystroke text analysis, are now economically viable to deploy. Chrome uses a unified architecture. 8 API endpoints, from summarization to translation, route back to the Gemini Nano model in VRAM. The browser layers distinct system prompts and decoders over these shared weights, allowing one 4 GB model to act as a specialized writer or translator. Developers interact with these endpoints through a standardized 4-verb lifecycle. First, you call availability to verify hardware support and monitor the model download. Once the weights are on disk, you call create to initialize a session. Execution typically uses streaming methods to keep the UI responsive, and once the task is complete, you must call destroy. This provides a predictable interface across all local AI tasks, allowing for simpler front-end state management regardless of the specific task being performed. When performing specific text transformations, you should use the designated task APIs rather than prompting the generic language model. Small LLMs are often inconsistent with formatting. Asking a 4 billion parameter model to generate a structured list often results in prose or invalid syntax that is difficult to parse on the client. To secure reliable data, apply a response constraint, forcing a strict JSON schema. The runtime blocks invalid tokens at the decoding level. This ensures the output is always valid JSON, removing the need for complex parsing logic or error handling loops. Using task routing and strict schema constraints turns probabilistic model outputs into type-safe data structures ready for production. Running LLMs on the client requires careful management of the GPU. Creating a new session adds roughly 300 milliseconds of warm-up time. Reinitializing the model for every single user interaction will make the application feel slow. You can mitigate this using a session singleton pattern, holding an active session in memory to reuse it across multiple inputs. Because an active session consumes VRAM, you must bind the destroy method to the unmount lifecycle. Leaving a session open after a user navigates away will leak GPU memory. You also face concurrency issues in real-time interfaces. If a user types quickly, multiple generation requests can overlap, causing older results to overwrite newer ones in the UI. The abort on input change pattern solves this. By passing an abort signal to the model, you can cancel an in-flight generation the moment the user provides new input. Managing these patterns correctly ensures that client-side AI remains responsive and stable without overtaxing the user's hardware. These implementation patterns allow for ambient AI, features that run constantly in the background. Because the marginal cost is zero, you can process every keystroke for grammar or sentiment without a cloud bill. This architecture provides a local processing environment where the data remains within the browser process. User information does not cross the network. This natively addresses strict compliance requirements like HIPAA or GDPR. By ensuring the inference happens on device, you remove the need for data residency engineering or third-party processor agreements. Real-time AI analysis is now a baseline capability for any standard web application, regardless of the team's cloud budget. To let an AI agent interact with a web app, developers traditionally had to build public APIs, manage OAuth flows, and handle the security risks of external access. The WebMCP draft, navigator.modelContext, allows a page to register tools as callable actions. An agent queries this schema directly, discovering actions without external routing. When invoking a tool, the agent authenticates via the existing session, bypassing API keys within the page's security context. WebMCP transforms web pages into dynamic tool services that agents can drive directly, simplifying the path to browser automation. Of course, local models do have clear limitations. A 4 GB model cannot handle the heavy, multi-step reasoning or the massive context windows offered by larger cloud LLMs. This necessitates a hybrid architecture. Cloud models handle complex logic and global knowledge, while the local browser manages real-time, privacy-sensitive interactions. This strategy beautifully balances the two environments, seamlessly connecting local, real-time speed with the heavy lifting and massive context of cloud-scale intelligence. Recognizing the browser as an inference runtime allows developers to offload significant computational costs and latency to the client's own hardware.